There you go. Does anybody know this word, latent heat?
Amount of energy needed to break it down.
Amount of energy to what?
To completely break it down.
No, not quite that. Not quite that.
Latent means remaining?
Yeah, I guess, or within.
Or within.
Yeah. No, we don't know this term, latent heat, do we? No? Okay, good, okay. So, right, so to get started, I'm going to give you a graph that they sometimes ask you to draw in the exam, roughly. Consider a block of ice which is slowly being heated. That is, a fixed amount of heat, delta Q, is being pumped in per delta T. For example, maybe 4,200 joules of heat is given to a block of ice per second. You know, something like this. You understand? You have ice and you have some heater, and the heater is providing constant heat per second. Yeah? What I want to look at is the temperature of the ice over time. Let's plot that. So on the y-axis I have temperature, and on the x-axis I have time. So the graph I'm going to show you is important. So, if you can't quite see it, I'll just read it here. All that's on the x-axis, is energy supplied in total. Okay, so at the very beginning you have no energy. Okay, then some time passes and you've provided 500 kilojoules, 1,000 kilojoules, 1,500 kilojoules, and so on. And the temperature for this ice is extremely cold. At the beginning it's at minus 100 Celsius. Now, what happens to the temperature as you put in more heat energy? It rises. But look what happens here. The temperature stays at zero, even though the heater is still putting heat into the ice. Now, this is very strange. And then it resumes. And then here at 100, even though you're putting heat into the container, it's staying at 100 and then it will rise again. So there's two parts of the graph where the temperature is not changing, even though more heat is going into the system. What is happening here?
Phase change.
Yeah, it's changing phase from solid to liquid, and then later liquid to gas. But what is the significance of the temperature not changing? What does that tell us?
Energy is being absorbed.
Yeah. In other words, to change from a solid to a liquid, you need energy. To change from a liquid to a gas, you need energy. It doesn't just happen because it gets hotter. It happens because energy is going in. So, example. Imagine you have your water with your ice inside of it. Okay? The ice is at zero and the water's at zero. So just because it's at zero doesn't mean it's ice. It could still be water. What is different between the ice and the water? Well, if you want the water to become ice, even though they're both zero, you need to take more energy out of the water. Or the opposite, if the ice is zero and you want to make it water at zero, you have to put more energy into the ice. In other words, simply put, changing the state requires energy. That's as simple as it is. In the exam, they sometimes ask you to sketch this. Now, they don't care about the numbers on the x-axis. You can just write energy. But of course, they do care about the numbers on the y-axis. That is, where should the first flat line be? Zero. And then the second one is 100. Also, what they care about is that this is much longer than this, meaning that more energy was required to move it into the steam than the solid to the liquid. Okay. Another thing that they'll care about is, let me see.
They put Kelvin on the other side. Do you have to do
Oh yeah, no, that's a bit over the top. Yeah, the other thing that's important for the graph, when you draw this, please make sure you have these three things right. Number one, that this is at 0 and this is at 100. Yes? You can't, it's too small, isn't it? Yeah. That this is at 0 and this is at 100, that's number one. Number two, when you draw this, make sure you draw this one longer than you draw this one. And number three, when you draw the slopes, make sure this slope and this slope is steeper than this slope. That the first and the last one is up steeper and that the middle one here is less steep. That's where you're getting the marks in the exam, for those features of the graph. Okay? Don't worry about the number in here. Yeah, Diego?
It doesn't have to be perfect, but like one more.
Yeah, it doesn't have to be. Like for example, maybe if I'm doing this in the exam, I would draw my graph like this. Here I'd put just energy in kilojoules, and here I'd put temperature in Celsius, and here I mark off maybe 100. Okay, and I have it going steep till it hits 0, and then I have a short line here, and then less steep than this one, and then see I've gone off the scale a little bit here, and then it's longer here, and then it should be roughly the same steepness as this, so it kind of a bit steep at the end here, and then I should mark off here 100. So if I drew that in the exam, that's full marks. That's everything they want to see. Yeah? Are we happy with that? Yeah? Okay, so I'll let you copy this into your notebook. Do you want to copy this one or my one? You could, write on some paper and then transfer it later.
I'm going to do it once later.
Oh, no, I don't know if I like this. Do I like this?
The video will be on YouTube.
But how will I know that you'll watch it and make notes?
I'll see the video in the morning.
Like, subscribe, and comment.
At least take out some paper to do any calculation questions I give you. You have no paper with you. You're paper free. Yeah, but what about other subjects? Oh, this is your only subject today.
Yeah, it's only
How come? What do you normally have in the morning?
No chemistry.
Normally we have a class from either 9 or 10 to.
Which is usually
4.
what?
chemistry and then you for one lesson.
Why not today?
They moved all the ones in Monday to down there, so
Maybe
that
the
our
rain is-
classes are longer than usual.
Oh, by the way,
Oh.
this week we have one more physics class. Can you see the timetable?
Like an extra?
Yeah.
7 hours?
Yeah.
What? That's outrageous.
We have like double Monday, double Tuesday, double Wednesday, and then Thursday we have one.
We'll probably turn that into an essay class, the extra one. Okay, have you drawn that? Right, so now on to the definition of latent heat L. Does anyone want to have a stab at the definition? The latent heat L,
The amount of energy
yeah,
required
yeah,
to change
yeah,
the state of
yeah,
a substance compound.
yeah. Nearly. You left out two things though. So, yeah, so we usually would say a unit mass,
Yeah.
but there's one critical thing you left out. And no, temperature. The latent heat L of a material is the energy required by a unit mass of the material to change its state to a different state without a change in temperature. In other words, it's only energy needed for only changing the state. It should not have any change in temperature. Half the students will forget in the exam in their definition to write without change in temperature. Oh, I see you had a change of heart, Zach. This makes me feel warm and fuzzy on the inside. Okay? Yeah? Now, a little further vocabulary. So, you know, you need energy to go from solid to liquid and liquid to gas. So there's different words for each situation. Latent heat of fusion is for between melting, basically, solid and liquid. And then latent heat of vaporization is for boiling. These are often, perhaps always, different numbers.
This is called fusion.
Fusion is like the fuse. I don't know, it's like the verb in English to mean to make solid. Do you know?
Yeah, but you're not fusing it, you're doing the opposite.
No, it's used in both directions. So it's the same latent heat for either melting or fusing. So, like, yeah, I understand. Equally, it could have been called the latent heat of what? How could we change?
Disassociation.
No. We want to change.
Because it's
What-
solid.
How do you change melting into adjective or something? Latent heat of something. Not meltion. Yeah, maybe it's just a grammar thing. I don't know. Can't think of anything. No matter. Okay, you got those two words, fusion and vaporization. So you can work out this very simple formula. The energy required to change a state of mass m, but not change its temperature, is simply m times L. That's all. Much simpler. So what's the unit here for latent heat? Have a look at the formula. What's the unit for L? Just do a bit of rearranging in your head. Yeah? Yeah? Go on. Yeah, joules per kilogram. Okay, so this formula you'll need. Got that? So, just to be clear, you don't have to write this down, just to be clear. Water will freeze at 0. Water will boil at 100. Now, you'll need to know this value. The latent heat of fusion for water is 334, and please note there's a kilo there. So it's 334,000 joules per kilogram. That's the latent heat of fusion of water. Now that's a big number. That means a lot of energy is required to melt ice. A lot.
A lot of things needs to be removed to make water
Yeah.
ice.
Yeah. know. I think it's easier to do. Well, I suppose you can do the other direction for free if you just leave the ice out in the sun. Okay, continue. The next one is the vaporization, which is even bigger. It's 2 million joules per kilogram, basically. You got that? Yeah? Yeah? And water could be a liquid at 100. And it is a liquid at 100 until it gets enough energy to become steam. Likewise, water could be a liquid at 0 until it loses enough energy to become ice. So 0 and 100 are interesting values because at 0 your water could be both liquid and ice, depending on where it is in the process. And at 100 it could also still be a liquid and steam. That's why if I have water here and it's boiling, bubbling, and steam's coming off, I know that this water is at 100. It can't be more than 100. Only the steam could be more than 100. Because if it went past 100, what would happen? It would definitely be steam. And I know it's not less than 100 because it's becoming steam. So by boiling water, I know it's exactly 100 in here.
I see.
Yeah. This is why, remember last week we did the experiment for the heat capacity. Do you remember where you put the metal in the 100?
What does
We know it's 100 for certain. Yeah?
what does boiling point change because of altitude?
Because of the pressure.
The pressure is what does it, but what's changing about the structure? I would guess that it's lower, isn't it?
Yeah, it is lower.
Because so the pressure,
2000, I think it's like.
the pressure must be giving it some energy. If you have it under a higher pressure, there must be more energy being in.
But that would mean
I suppose
the
the question.
vaporization point would be lower as well.
I think
So
it
it
should,
requires
shouldn't it?
less energy to become a gas.
I would think so. Is
At
it not?
different temperature.
Yeah, the temperature which becomes a gas is different, isn't it?
Yeah.
Is it less?
Yeah.
Less.
Yeah, because the pressure must act in such a way to assist in giving it energy. I suppose think about it like this, you know, which is easier to break, a rope or a rope that has something hanging on it? Do you know what I mean?
Yeah.
I kind of think about it like this. So the gas being at the pressure kind of makes it easier to bring it to a different state because the bonds are already under extra strain. I'm not sure actually. I've never really thought about it too much. It's not something that actually comes up in this course. The fact that it changes at different pressures. But you're right, it does. It does. Okay, continue. Yeah. So, just to be clear, imagine a block of ice that's at -20 and you put it in a microwave. What will happen? Well, first it'll be at -20, right? And then it will increase to 0. But it's still solid at 0, still ice, until it melts. And then it will become water. But what temperature will the water be? It will be 0 at first. Then what happens? It will warm up to 100. It will still be a liquid at 100 until it boils. And then it will become steam at 100. And then the steam will start to warm up if it doesn't leave the microwave. Okay, so you don't have to write this down. I really want to make it very clear what happens. Okay, it's not like once it becomes 100, it magically becomes steam. Still, it needs more energy. You get the picture? Yeah. Okay, so let me give you a small question to try. How much energy do you need to bring 1 kilogram of ice at 100 to steam at 100? Now, before you start, you actually need to break this problem up into stages. So what's the first calculation to do?
Energy from ice to
Yeah,
fusion.
ice to liquid. Then the next stage.
Vaporization.
No.
It's the increase.
Yeah, increase. Yeah, from 0 to 100, and then the next stage.
100 to vaporization.
Yeah, vaporization. We just say yeah. Okay. Give me that calculation. And while you're doing that, I'll check something here for you. You think you have it? Should be a pretty big number. Yep. Yeah, okay. Okay, we got that. So, let's see. The total energy needed. First, we have to do the
Fusion.
solid to liquid. So that's fusion. I'll just write F here. And then we need the MC delta theta. And then we need the ML vaporization. So what's the M here? It's 1, isn't it? And fusion is 334
334
kilo.
Yeah.
And then MC delta theta plus M, and then what's the next one?
2265.
2265 000. So what did you get?
3.0171 times 10 to the power 6.
Joules. So it's basically 3.02 megajoules. Just to give you an idea, that's a lot of energy. I think like 1 kilogram of ice come steam doesn't seem like a lot, but it is a lot of energy. I think in Ireland, 3.6 megajoules will cost about 20 cent. Maybe a little bit more, 25 cent maybe. So, you do that 4 times and that's €1.
Making tea.
Yeah, well, I suppose you don't put, you wouldn't put ice in the kettle to make your tea. But it just goes to show you that, as soon as you're producing steam, you're using a lot of energy. Because the reason this is so big is really, okay, these were big too, but a lot of it's coming from the last part, Okay, let's see, next. A 200 gram cup of water has 10 grams of ice added to it. They're mixed together and reach thermal equilibrium. How much energy will be required to bring the mixture to 10 Celsius? So we know at the beginning, this is our picture, we have water and ice. 200 grams of water and 10 grams of ice. And what's the temperature of each? 0 Celsius and 0 Celsius. And then what happens is this becomes just water at 10 Celsius. And for me, it's helpful to imagine the ice is still like here, but it's just become water in the middle. Obviously, it mixes together, but for my mind, it's easier to think about it like this. And my question is, what was my question? I forgot. Oh, how much energy do I need to go from here to here? So how much heat do I have to put into this system to take it from here to here? Okay. Well, let's do it in two parts. Let's look at first how much heat energy is required for the water. So the water, we have 200 grams. And what is the change in the temperature of the water? 10. So that's fine. Now, let's look at what's happening to the ice. The ice is doing two things. Firstly, it melts. What's the ml?
Well, 334.
334. But then the ice does a second thing after it melts. What's that? Rises to 10, yeah. So, by adding these two numbers together, I can get the total energy needed. Okay, can you try that then? Oh yeah, 12,120, is it?
Yeah.
So that's 12.1 kilojoules. Is that okay, folks? You happy enough with that? Continue. Right, now, that's the next one. Some ice at 0 was mixed to 330 grams of water at 15. The ice and water was mixed until the ice melted. The final temperature of the mixture was 5. How much ice was added? So, here's the picture. I've got some water. What's the temperature of the water? 15. Put some ice in. How much? Don't know. Mix it together. Ice melts. Final temperature, 5. So, how much ice did I put in? Right, this is a harder one. Let me draw the picture for you. So what you have is this. 330 grams of water at 15. And then you have ice here, but you don't know how much. Let's say it's X kilograms. And we know that that's at 0. I'm sorry if I didn't say it's at 0. I did say it's at 0. Then you mix this all together and you end up with your 330 grams at 5 Celsius. And your ice, which is X grams, is now at also 5 Celsius. And we have to figure out what the X is. Okay, so before I do this, do you all understand what the problem is? Yeah? We've seen one like this before. The water, is it gaining or losing energy? And the ice? Gaining. There's no other energy being added to this system. So what that means is the energy gained by the ice, that will equal the energy lost from the water. Okay, so how much energy does the ice gain? Well, two things happen to the ice. What's that? It melts, so that will be M, which in this case is X, L, which is 334. Then what does the ice do? After it melts, it increases. How much does it increase by? 5 degrees. And this energy the ice gained came at the expense of the water. The water was at 15 and is now at 5. So that will be M, C, and the 10. Now, when you write the equation down, you realise, oh, it's not so bad. I can get the X. I can just do a bit of a cross multiply. This will be 3.3 times 4181 over 334,000 plus 5 times 4181. 0.0388, so 9 grams, because that's in kilograms. You get the idea for this one? Yeah, continue. Zach, yeah? Okay. Water of mass 250 gram was added to a copper cup of mass 25 grams. The water was stirred until all the water and copper were in thermal equilibrium. The temperature X was recorded. An electric heating element was placed into the water. It took 2 minutes for the 5.5 kilowatt electric heating element to boil off the water. Assuming no heat loss, calculate the X. Alright, now let me draw this, what's happening here, okay? So, and I'll let you try this one. You've got a copper cup. This is my cup. This is copper. How much? 25 grams. And you put in it some water. The water is 250 grams. Okay. Now, both of these are at some temperature X, which you don't know. Okay. And then what you do, you come along and you put some heating element here, make some heat. The power is 5.5 kilowatts, and you run this for a total of 2 minutes. And after the 2 minutes, what you are left with is nothing. The last bit of water boiled away. It's completely empty now after exactly 2 minutes. So this is the picture later. It's all gone, empty. And my question is to find X. Now you'll need to look up the heat capacity of copper, which I gave you in the last class. This is now empty. close that?
There. Blind.
Going further now.
What's that?
Perfect.
Can I take a look at the question?
Yeah. Did I get all the info right? Or am I missing something? And just to be clear, I know it might seem stupid, but I think it does really matter. The heating element actually is inside the water. So I know I make it look like it's outside, but really, I don't know if I say it in the question, but the heating element is going inside. Oh, what the heck? Come back, pen. The heating element is inside the water here. Okay.
The delta T be 100 minus X.
The delta T would be 100 minus X. Question? Sure.
And it's 25 grams.
Have you got that, guys?
Not yet.
I flick to the paper. Any ideas?
Doing algebra.
Got that? Got an answer? No? What'd you get for X?
No, I haven't finished.
Impossible?
No.
No, it's a long algebra.
Let's have a look. Okay, so power equals work. Look at my handwriting. Sorry, I'm very low on energy. More coffee needed. Whew. Okay, let's try that again. Power equals work over time. So work equals power multiplied by time. So the work being done is the heat. So the W equals the delta Q. And that will be 5500 times 120. That's the delta Q. By the way, what is that? Delta Q equals
660 pounds.
like that. Now, where did that energy go? Well, a few things had to happen. Firstly, the copper needed energy to go from its current temperature of X to its final temperature of 100. So that would be, now, why do we know the copper's at 100? Yeah. But why couldn't the copper be more than 100? Could it? Could it? Which way is the heat flowing? It's flowing from the water to the copper, not the copper to the water. So the water must always be hotter than the copper. Remember our second law of thermodynamics? The heat flows from the hot to the cold. So the water must be hotter than the copper until perhaps it reaches thermal equilibrium, and then they could both be the same. But the copper can't get hotter than the water because the heat is flowing from the inside to the outside. Okay, if the copper was hotter than the water, then the heat from the copper would flow back into the water. It can't flow that way. Do you understand what I'm saying or not? No? If which way is what's the heat source here? The coil, which is in the water. So which way is the heat flowing? Is it from in to out or out to in?
Now I see.
Yeah. So M. What's it? 385.
Yeah.
C. And it's correct. 100 minus X. Now, what happens to the water? The water does two things. First, it gets to 100 from its temperature currently of X. So that's M. Yeah. C. And also 100 minus X. Right? And then it's M
times 2265.
2265000. Now, for those who want to save effort on the algebra, okay, do you see here there's a common 100 minus X here? So what you can do is you can do 660000 minus 0.25 times 2265000 divided by 0.025 times 385 plus 0.25 times 4181. What will that give me? 100 minus X. So if I rearrange this a little bit, if I did then 100 minus this, I'd have the X. So X equals that fraction there. Which equals, you can see what I've done. I've saved a lot of algebra work here. Just rearrange it, you got X equals this. So what is that? Now we really want this number to be more than 0 and less than 100. Ah, no, what? What's the number?
Maybe negative
Five.
721.
531,
Oh,
63.
can you hand me your calculator, please? Let's see if it's me that's the problem or my students.
We're not putting brackets around the paper.
No, dudes, you guys don't know how to use calculators. What's your problem? I got 11.1 Celsius. I need like some kind of internet meme here that would be suitable. What could I use? Yeah. Did you get it? Do you even calculator, bro?
No, I write solve and give you.
Oh no. I don't like hearing these sounds. You all understand how calculators work, don't you? Yeah.
I put a 0, 0, and 1, 1.
Did you get it now? Yeah. What's so difficult about looking at something and typing the same thing on the calculator? Is it that the task is too simple?
I wrote 25 instead of 0.25.
Okay. Yeah, okay. So why did you think I put the 0 there?
I did solve the point 25, that's all.
Okay. But still, that means you thought your teacher wrote 025 for 25. Do you know? How old are you? I'm 018. No? Oh, that's okay. I forgive you. You got it in the end, yes? Yeah. Did you get it over here, Dorian? You're not making the satisfying sound of getting it. Did you get it? Or you still don't got it? Are you sure?
No, it's just, well, I'm good at it, but I wrote the stick wrong down. What was it?
Did you get it? Gina, is this okay? Is that yes or no? Gina? Every second that passes hurts me on the inside. Maybe I typed in something wrong. It is this.
It's
No, it gave me the idea.
But Lynn says 10.39. Why is that? Maybe I did. You know, it'd be terribly funny if I typed in something wrong after me going on about where. Can't you type in on the calculator?
It gave me 11 point.
Oh, there you go. There you go. It's not. Sorry. It's not 38.5. It's 385 in the bottom. There you go. All right. Are we all right now? Are we sure?
Sure. It should.
I don't. There's a cloud of confusion over this side of the room.
Those guys are new, right?
Huh? What? Good, bad? You got it? Oh! Let's have a look. What did you type in? Well.
Her calculator is messed up, so because it doesn't show as a fraction, like over a line.
No,
Yeah.
I just didn't put the kilos.
You didn't put in what?
It should be,
Oh, she doesn't like you can't
Kilo. Kilojoules, yes.
but I didn't put it.
Ah, okay. So you're fine. Are you okay?
I'll be fine.
Are the glasses too tight on your head? I think I agree with Zach. I don't like these calculators because they're more difficult to work with. And these are a little.
Instead of,
Yeah.
it's so hard to see.
Let's have a look. Let's have a look. Look.
I,
Let's go. Watch it.
Instead of showing
660
that-
minus
Yeah.
0.25 times
like this. 1.
2265.
Yeah.
Oh.
It all writes it on one
Divide by bracket 0.025 times 3 and 5 plus 0.25 times 4181 close bracket, and then it's going to be 100 minus that answer, and there you go, 11.1. Okay.
Why did they kill me?
Right. So, let you try a couple of these for a few minutes, and then we'll have a start on the next lesson. And how big is the next lesson? Let's see. Yeah, okay, we'll probably get just some of it done.